Ideal gas law. So we can take all those relationships, Boyle's law, Charles' law, and Avogadro's law, and we can combine them into one equation. If you're interested in how that works, the actual math of that, I'd be happy to talk to you about it. I'm not going to go over it in a lecture because I know that most of the students just really don't care. And that's fine. I'm not going to make you derive it. But this is the bottom line. This is the ideal gas law. PV equals nRT. That one's really important. Some people remember it by calling it PIV-NERT. PV equals nRT. So we've got some familiar things here. We've got pressure, volume, number of moles, and temperature, and then we've got this R thrown in there. R is the ideal gas constant. And the value of it depends on what units we're using for pressure and volume. So the one that we're going to use the most often is R equals 0.08206. And then the units on that are going to be liters, atmospheres, divided by moles times Kelvin. And that looks like a mess of units. But those units tell us that we need to use atmospheres for pressure and liters for volume. We always use moles for N, and we always use Kelvin for temperature. So this is something else you should memorize. Oops. 0.08206. Liter atmospheres per mole Kelvin. Any questions? Flashcards. This kind of goes over how those equations relate together. One thing I would like to show you here is how you can use the ideal gas law to get any of the other gas laws. So what I'm going to do is I'm going to put subscripts on the ideal gas law. R doesn't get a subscript because it doesn't change, it's a constant. So P1V1 equals N1RT1. Well, if I divide both sides by the same thing, then it's still equal, right? I divide the left side by P2V2 and I divide the right side by P2V2, it's still the same. But the ideal gas law tells me that P2V2 is equal to N2RT2. Okay? What's R over R? 1. Cancels out. So now we're left with this mess. What if we just have pressure and volume changing, and the amount of gas is constant? If the amount of gas is constant, then N1 is equal to N2, and those cancel out. If the temperature is constant, the temperatures cancel out because T1 is equal to T2. Now what's the right side of this equal to? It's equal to 1. If we cross multiply, we get P1 V1 equals P2 V2. And there's Boyle's law. You can get Charles' law, you can get Avogadro's law, you can get Gay-Lussac's law, and you can get what's known as the combined gas law, where pressure, volume, and temperature are changing. You take the ideal gas law with subscripts of 1, you divide by the ideal gas law with subscripts of 2. You cross out anything that doesn't change, and then you rearrange the rest of it for the thing you're trying to solve for. So you can memorize the ideal gas law and how to do that, or you can memorize the ideal gas law and the other gas laws. It's up to you. Okay, let's do an ideal gas law problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure, and they want it in atmospheres and PSI, of the gas in the tire? Well, how have we been approaching these problems? We make a table. Well, let's make a table. Because what happens now that we're getting through all these gas laws, they're going to give you I will give you a gas law problem on the exam, and you're not going to know which gas law you need. You can always do the table. This time we don't actually need the table, but it's not going to hurt anything. So when we did the table, so we have row 1 and row 2, and we come across numbers, we write them down, and we identify them. So first number, 8.50 liters. Is that P, V, N, or T? It's volume, because liter measures volume. So there's our volume. The next number is 0.552 moles. What's that? That's going to be N, amount of gas in moles. Temperature of 305 Kelvin. Oh, that's nice. They gave it to us in Kelvin. We don't have to convert it. How thoughtful. Temperature. We ran out of numbers. There's no second row. It's okay. I'm just going to erase the rest of this stuff. Did making that table hurt anything? No. We just identified what we've got. We've got a volume, we've got an amount of moles, an amount of gas in moles, and a temperature in Kelvin. They're asking us for the pressure. Nothing's changing. The simple gas laws, Avogadro's, Charles, and Boyle's, are for when things change. You heat it up, you expand it, you compress it, you do something to it. Ideal gas law is just you've got a thing, and nothing happens to it. You just want to know something else about it. So this is ideal gas law. Oops. PV equals nRT. We're looking for P, the pressure. So we have to rearrange this to solve for pressure. I should cancel those out. So the pressure of this gas equals nRT over V. We have N, T, and V. R we need to memorize. So N is amount of gas in moles. Write the units. R, 0.08206. Write the stinking units. Liter atmospheres per mole Kelvin. I know it's tedious. 305 Kelvin is our temperature, and then we're dividing by volume, 8.50 liters. Before you calculate, check the units. Well, here I've got moles and moles. Those are going to cancel. I've got liters and liters. Those are going to cancel. Atmospheres, no, there aren't any atmospheres. Kelvin and Kelvin, those will cancel out. I'm left with atmospheres, which is a unit of pressure. That's looking good. 0.552 times 0.08206 times 305 divided by 8.5 equals, so pressure equals, I should have 3 sig figs, but I have to convert units also. So 1.62, there's my 3 sig figs, 54 atmospheres. It also wants this in PSI, so I need 2 answers. So my first answer is it's not very good, 1.63 atmospheres. And then to convert this to PSI, I need a conversion factor. This is not one you have to memorize. You're going to put ATM on the bottom. You're going to put PSI on top. 1 atmosphere is 14.69 PSI. I just remember it because I've used it a lot. So I'm going to take that pressure in atmospheres and multiply by 14.69. And that's going to give me 23.87664486. But again, 3 sig figs, 23.9 psi. Question asks for 2 things. You need to give 2 things. In lab reports, there's a lot of, number 3, and it says, what is this, or why, or whatever, yes or no, explain. You got to explain. Or it'll ask you, what's the most and what's the least? It wants 2 answers. And you may think I'm getting really picky when I count it wrong because you didn't answer both the questions. You know what happens if you go out for a big job interview? You're going out, you're trying to get a job, and you're sending out resumes and filling out applications. They are really, really picky on those applications, and if you don't answer all the questions, you're just not even going to get through the first level. And so this is something we need to learn. Any questions about this problem? Another ideal gas problem. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So you may be able to look at this and say, there's nothing changing here. I'm going to need the ideal gas law. I don't really need to make a table. That's fine. If you don't recognize that, go ahead and make the table. You'll have 1 row, and you'll have identified everything. I'm going to do it without the table this time. So 0.556 moles and 715 millimeters of mercury and 58 degrees Celsius. I need to label these. Moles, that's N. Millimeters of mercury is a unit of pressure. And 58 degrees Celsius, that's a unit of temperature. Units are your friends. I'm finding volume. I need the ideal gas law, PV equals nRT. I need to get volume by itself, so this time I'm going to divide by pressure. Volume equals nRT over P. Well, let's plug things in. 0.556 moles, include the units. Ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. The temperature, 58 degrees Celsius. I'm just writing in what they gave me. We do have to convert to Kelvin. I'm playing dumb here. So I just plugged everything in, and then I just calculate, right? No. Look at the units. Okay, so we got moles and moles. Those will cancel out, great. I've got atmospheres and millimeters of mercury. That's not going to work. The easiest thing to do is to convert this to atmospheres. So this is a conversion you should have memorized. We want atmospheres up here, and we want millimeters of mercury down here. How many atmospheres to how many millimeters of mercury? 760. 1 atmosphere is 760 millimeters of mercury. That is an exact conversion. So 715 divided by 760. That's going to get me 0.940. I had 3 significant figures in my original number there. I'm going to carry 2 extras because I don't want to have some rounding errors. So 94079 atmospheres. So I'm going to go down here and I'm going to erase that and write in atmospheres instead. Oh, there, that's better. ATM's canceled. Degrees Celsius and Kelvin. No, not going to work. I need to convert. So I'm going to add 273.15 to my 58. It's going to give me 331.15 Kelvin, but that only has 3 significant figures. So I'm going to erase that and put in 331.15 Kelvin. And now the kelvins cancel out. There we go. The units on the ideal gas law are going to tell you what units the pressure, the volume, and the temperature have to be in. The ideal gas law does not show up in the simple gas laws, Boyle's, Charles, and Avogadro's. They're the only unit, I'm sorry, there's 2. Temperature has to be in Kelvin, and N has to be in moles. But the pressure and the volume could be in different things. Ideal gas law, we have to have atmospheres and liters. Okay, so now we can do our calculation. 0.556 times 0.08206 times 331.15 divided by 0.94079. This is my final answer, and so I can round it. I should have 3 significant figures. I'm going to get 16.1 liters. Any questions? Yes?
You said the 760 for converting it to ATM was you have to memorize it, you said?
Yeah, you need to memorize that.
Is it just for the element, or is it for universal?
It's for mercury, 760 millimeters of mercury, but we won't run into anything else.